The Frumkes Center for Writing and Culture at Hunter College presents 10 years of best-selling authors and great thinkers. Each week we broadcast new videos from our 10-year speaker archive online for free at our website. We look forward to seeing you again when it's safe. Please enjoy this presentation from the archives of the Frumkes Center for Writing and Culture at Hunter College.
Good evening. My name is Louis Frumkes. I'm the director of the Writing Center here at Hunter, CE. And as you know, tonight is the conclusion of our Great Thinkers series, which I hope many of you attended and heard Seth Lloyd and Steven Pinker and Rebecca Goldstein, etc. And on the 21st, we have Stuart Woods coming, who will wind up our best-selling author series. And that is actually the last event until June 9th, when we have our Writers' Conference. And there you, if you would like to learn what's going on in the publishing world, whatever, it's like a Wild West show, but we have panels that will explain it to you. And you'll meet the likes of Francine Duplessis Gray, and Peter Straub and Mary Higgins Clark and Daphne Merkin, et cetera, and you'll have a wonderful time. So I think the brochures are on your chairs. And tonight I'm actually very excited to have Lisa Randall here. She's a rock star in physics, very difficult to attract down here, and I was just very, very fortunate to get her. And she's been traveling like a dervish, but here she is for whatever reason. So I'll tell you a little bit about her. When I was a kid I read Flatland, which had a profound effect on my thinking. It allowed me to think of the possibility of other dimensions. Squares and triangles inhabited the social strata of Flatland, but they lived in a two-dimensional world and couldn't conceive of someone like you or me, especially me, from the third dimension. Now, along comes Lisa Randall, who has proposed the possibility of other dimensions beyond the four we are familiar with. But Lisa Randall is no kid reading Flatland in the library. She is a professor of physics from Harvard, particle physics, who Time magazine has named as one of the most important scientists and thinkers of our time. Lisa won first place in the Westinghouse Science Talent Search while at Stuyvesant High School and was made a fellow of the American Academy of Arts and Sciences in 2004. In 2006, Newsweek magazine called her one of the most promising theoretical physicists of her generation. She has done important work in supersymmetry, Standard model observables, cosmic inflation, baryogenesis, grand unified theories, and general relativity, and is probably best known for the Randall-Sundrum model, which she published in 1999, and which shows, among other things, that our world exists in a three-dimensional brain, that's B-R-A-N-E, like membrane, within a higher dimensional universe. In fact, her list of awards and achievements are far too long to cite here tonight, but suffice that she has written 2 books, Warped Passages and Knocking on Heaven's Door, which she will be happy to inscribe for you after her talk this evening. It gives me great pleasure to introduce Lisa Randall as the Writing Center's final speaker in our Great Thinkers series this year. Lisa?
Good evening. It's a pleasure to be here. And the only thing that's not a pleasure is I forgot my power supply. So this talk might be interrupted at some point. You see it's telling battery stretch now. So I'll try to get through some of it, but it's going to be a little bit of an issue perhaps. So I'll try not to make it too long, but it is a slightly longer talk. What I want to tell you about today is, battery stretch yet again, is basically some of the stuff that I'm covering in this book, Knocking on Heaven's Door. A lot of people ask me about the title, which I guess is not a surprise. Anyone who read my first book knows that I tend to have song lyrics stick in my head. So when I'm sort of thinking about various ideas, a song lyric comes to my mind. So this one came to my mind for the title. But what I was trying to express with that is the idea that we sort of have this core body of knowledge and that we try to stretch beyond it. That's what scientists do. We don't just throw things away. A lot of people misunderstand the kind of work we're doing, and I'll tell you, it's very abstract in many ways, but it is real, ultimately. And what we're trying to do is extend the knowledge that we think we have and see what really underlies it, what's at those edges, and that's what I was trying to express. And the subtitle is How Physics and Scientific Thinking Illuminate the Universe and the Modern World. And what I was trying to express there, and as you can imagine, my editor really wanted to make sure there was a good subtitle, because he's like, no one's going to know what this book is about. But what I was trying to explain there is that I'm talking both about the physics that we're doing today, the physics of very small, tiny particles, the physics of the universe, cosmology. But also, I really did write the book in large part because I actually didn't like the way science is often presented. And if you hear the debates about science, it's not just that people don't care. They really just genuinely don't understand what science is a lot of the time and how it really works in practice. So what I wanted to do in this book was I had some chapters that were about the actual physics, but a lot that were about the methods of science, and not just a sort of very pristine view, but really how it is when you're in the trenches, in the sense of what role uncertainty plays, what role scale plays, which I'll talk about today, risk, creativity, which is often undervalued. So that's what I tried to do, and that's what I'll tell you a little bit about today. And it's a relatively small audience here, so actually this is very unconventional, but I don't mind if there are questions in the middle, because it's silly to get stuck in the middle. It's like in a science lecture, once you lose it, then you're usually gone. So I really don't mind if anyone wants to raise their hand and ask a question. And neither will anyone in the audience, right? Okay. Okay, that's because it came out in Germany last week. Okay, so I'm going to start with a picture which looks somewhat random. I think most of you can recognize where it's from. Somebody sent me this picture. So you see the Eiffel Tower in the background, and you see a kiosk with an affiche, a poster on it, in the foreground on the right. And of course, these are some identifying features of Paris. But why am I showing you this picture? Well, I want you to think about the fact that when you look at that picture, actually, the scale with which you're looking at it really matters. If you didn't have the resolution to see that the Eiffel Tower was there, if you were looking from an airplane, or if you just didn't have a lot of resolution, you just wouldn't even know it was there. And of course, that's not just a metaphor, but that's really the way it works in terms of the physics of elementary particles or a lot of science. Until we have the tools to really get to scales, to see scales that we can otherwise not observe, we don't know things are there. They're there, we're perfectly happy, but we just don't know about them. And of course, if you have more resolution, if you're looking up close, you'd see the fine iron gridwork on the Eiffel Tower. And if you had tools to look even closer, you'd see the actual atoms of iron, etc. So what I want to get across here is that scale and resolution really matter when we think about the physical world. It's a really obvious point, but we often forget it. And we forget it when we think, how can the world be made up of atoms and quarks at the same time, and atoms and quarks in this block of wood? I mean, it's because these things appear at different scales, and what you're going to focus on depends very much on what resolution and what tools you have at your disposal. Now, of course, the reason I really showed you that slide was because if you blow it up and really take scale seriously and blow up and look at the affiche, you actually see my name on it. And that was because I wrote the libretto for a small opera that premiered at the Frumkes Center based on some of the ideas I'll tell you about later, which, and I'll tell you, if there's time, I'll tell you a little bit about that too. But I want to come back and just remind ourselves that our intuition is guided by human scales. I mean, we see things we see with visible light. Visible light has a very definite spectrum, and it gets processed through our brains and all this. We basically see from a millimeter to a kilometer if we don't have any other tools at our disposal. We don't see much smaller than that. We don't see much bigger, generally speaking. And those are kind of the scales that we're familiar with. The physical universe, of course, involves a much bigger range of scales. It doesn't mean it doesn't exist because we can't see it. That's a feature of us. That's not a feature of the universe. So the challenge to physicists is, of course, to find the tools and methods and theories that apply at these scales that seem unintuitive because they're not what we encounter in our daily lives. So before I do anything else, I'd like to just start off with a very brief tour of the universe just to sort of set the context and the scales involved. Okay. So I'm going to start off with large scales. Notice that there's a human being at the bottom. That's about a meter. Okay. So that, it's not a coincidence that we measure in meters. It'd be really weird if we were measuring in the scale that corresponds to 10 to the 5th meters, because most of the scales we see, if we look at our arm or something, we see scales are about a meter. Most of us are about 2 meters tall. Most of us are a little shorter. But the known universe is enormously bigger than that. 10 to the 27th meters. That's a 1 followed by 27 zeros. That's a lot bigger. That's 27 factors of 10. You might ask why I say it's finite in size. Isn't the universe infinite? And in fact, the universe very likely is infinite. But I'm very much focusing on what we can hope to observe in this talk. And what we can hope to observe is finite. And that's because the age of the universe is finite, 13.7 billion years, and the speed of light is finite. So if we literally want to observe or see something, and we believe nothing goes faster than the speed of light, we're not going to be able to see beyond this known universe of 10 to the 27th meters. Now, I do theoretical physics. I'm not completely limited by what people can observe or do experiments with. So I can speculate about what lies beyond that. But we have to keep in mind that these are things we won't be able to verify through observations or through experiments. Now, within the visible universe, there's a lot of things that happen between the scale of 10 to the 27th meters and a meter. There's all sorts of objects. There's galaxies at 10 to the 20th meters, the solar system, 10 to the 13th meters, the Earth, 10 to the 7th meters. So there's all sorts of objects of different sizes as we go through the universe. And a lot of it's just empty space, but there are objects within it. One thing I want you to think about, though, is that even though all these different scales are involved, they all use the same laws of physics if we're trying to understand it. We're using gravity, we're using electromagnetism. The laws of physics don't change even as we go from 10 to the 27th meters down to a human scale of a meter. And I emphasize that because now I want you to think about small scales, which is actually, for some reason, much less intuitive for most people. So now we're going to continue going down in scale. So now the human being, who's about a meter tall, is at the top of this plot. And we're going to go down. And I actually start off by telling you about some biological things, not physics things, because I really want you to think about the fact that we didn't know what was even inside our own bodies until the tools were developed to really look at smaller scales and find out what's there. You might think we're all really smart and can guess it all, but we didn't even know about the circulatory system till bodies were cut open and arteries and veins were found. We certainly didn't know about red blood cells until you could put blood under a microscope and see them. And certainly DNA was identified in part because of X-ray diffraction, so that the double helix was found. Okay. So it's very nice to believe as a theoretical physicist or that we can just predict everything that's there, but in fact, the history of science is a combination of people figuring out what's going on and observations being made. And I emphasize that because I think a lot of the time in popular science books, that's lost. I mean, this sort of, this is all just so beautiful and wonderful and awesome and we should all admire it. But really, it's messier. You have this back and forth between making observations, saying, wow, I never thought that would be like that, and then trying to figure out what it means. And that couldn't have been more true than the atom. You might say, well, of course we knew about the atom. The Greeks knew about the atoms. But first of all, the Greeks' atoms were unchanging, indivisible objects. And the way atoms were actually found is, oddly enough, because they can change. That's why they emit spectral lines. And because they're divisible, so we could see the nucleus and the electrons. Had they been unchanging, indivisible objects, it would have been longer before we actually found them. And within those atoms are nuclei surrounded by electrons. And then we can just keep going down. As we can see smaller and smaller scales, we can ask what's inside matter at smaller and smaller levels. So nuclei are made up of protons and neutrons. Those protons and neutrons are not themselves fundamental either. They have substructure, which is to say they have more elementary particles called quarks, held together through the strong nuclear force, which is communicated by particles called gluons. And one thing to notice here is that when the atom was discovered, it wasn't just the atom that was discovered. Quantum mechanics was eventually discovered, in the sense that quantum mechanics really rules the physics of an atom. And unless the experimental evidence for quantum mechanics had been found, no one would have guessed it. Even when they had the evidence right in front of their eyes, all the leading physicists found it really hard to believe quantum mechanics was right. It really was the experiments and this data that told them what's there. And the reason I'm emphasizing that is because I study the physics of elementary particles. And a lot of the time people think it's just a question of just finding smaller and smaller stuff. But we're not just looking for smaller stuff, and by that I mean my experimental colleagues. We're really looking for the underlying laws of nature. So the hope is to find smaller particles and understand what it is that guides them. For example, inside the protons and neutrons, there are quarks, and they're held together by the strong nuclear force. And the strong nuclear force was found when quarks were identified, and when all of this was put together. And right now, we're at an exciting frontier, because something called the Large Hadron Collider, the LHC, is running. That is basically studying the scale 10 to the minus 19th meters. Okay? That is a very small scale. It's a very high energy and a very small distance scale that's being studied. And what that picture is supposed to indicate is the Large Hadron Collider, and I'll tell you more about it, is based on a ring 27 kilometers in circumference. That's why it's called large. Hadron is actually a fancy name that includes particles called protons. It could have been called the Large Proton Collider, and people would have known what that meant. But it collides together particles called hadrons, which are in this case are protons. And it collides them. And so what you have is this, it's about 100 kilometers underground. You have this tunnel. Protons get accelerated to enormously high energy. Magnets divert them so that then they hit each other. And when they hit each other and they collide, in principle, new forms of matter can be made through the beauty of E equals mc squared. Because if you have more energy, you can make particles with bigger mass m. And that's the idea behind these experiments. And I'll tell you more about it. And I just want to say that that's not the end of the line in terms of distances we can in principle think about. So again, we're in a situation where this is the limit of what we're studying with experiments, pretty much. 10 to the minus 19th meters. But in principle, as a theorist, we can think about much smaller scales. And probably a lot of you have heard about theories of quantum gravity, such as string theory. If you haven't, don't worry about it. But people try to study what's happening at even smaller distance scales. At the scales we see today, we don't have to worry about string theory in the sense that it's not going to make a difference in terms of the predictions we can make. We're not studying string theory directly at the Large Hadron Collider. We are studying some very interesting questions, which I'll tell you about. But there probably is a limit to the distances that we will think about, and it probably is this distance called the Planck length, which is 10 to the minus 35 meters. And if there's time, I'll say a couple of words about that too. So what do we notice about this? Well, there's a lot of things. There's a lot of cool stuff as we go down inside matter. But the other thing that's kind of interesting, at least to me, is that that's 62 orders of magnitude in scale, and we even have different physical descriptions entering at different scales. So how do we keep track of all this information? How do we really need a theoretical tool to organize all of this. We want to concentrate on sort of the effective quantities relevant to anything. And so I'm just emphasizing this because I think it's an important rule that we use when we're thinking about science, but also when we're thinking about lots of different things. And it helps understand how we as physicists are thinking about the universe. And it's a lot like what you do when you use Google Maps. I should have put this location here. It's actually, the slide is back from when I spoke at the 92nd Street Y. But, sorry, it's close. but my point is that you don't need to have the detailed street map if you're coming, say, from Brooklyn. You know, you want to figure out roughly where you're going. It's only when you get into the neighborhood that then you're going to look you're going to zoom in and look at those details. And the reason you do that is because it really wouldn't make a difference if you had, I mean, it's not wrong to do that. It's an approximation for sure, because you're not putting in all the information about every single street. But it's a good enough approximation. You're not going to go take a wrong turn because you didn't know where 91st Street was. So it's not until you actually try to find the doorway, entryway, that you have to zone in on those details. And it's useful to think of this as the way we're thinking about science in many ways. When we're thinking about science at human scales, we mostly can ignore quantum mechanics because it's not making a difference at the scales that we're doing. Classical mechanics is right. I remember in high school, I was told that Newton's laws are wrong. And, you know, many years later, I understood that they're not wrong, they're an approximation. We know that ultimately, I see a high school friend of mine here, so she probably also heard this. Ultimately, these laws break down. And you find that they are not adequate. But the whole challenge to physics, the whole reason it's so hard to get this technology, is you really need to be able to get to these smaller distances or have the resolution. Otherwise, you'd never know it's there. So the fact that it's invisible actually is very pragmatic in the sense that it allows us to live our lives without knowing all the ultimate stuff that's inside. We don't have to think about that all the time. But it's also what makes science challenging, because you want to have the tools at your disposal to be able to study these small distances, which is why we're stuck building these enormous high-energy colliders if we really want to know what's going on at scales of 10 to the minus 19th meters. And I'll just point out, since this is the writing program, that this is a very general way of organizing your thoughts. And I don't have to tell you that there's different ways you can do reading. There's different ways you can think about how brains work and how people think. You always have the big picture versus details in just any way, because, again, we can only keep track of so much information at a time. So it's a very useful technique. We just don't even think about it, but we're doing it all the time to sort of zone in on the information that's relevant to the problem at hand. And, of course, it wouldn't hurt for other issues as well. So in physics, though, of course, it's something like if I threw a ball, this is more or less what I've said, quantum mechanics is more fundamental. Ultimately, it's made up of atoms and molecules, but we don't need to think about it if we project where that ball is going to land. Newton's laws work just fine. And the reason it works so well is because we just don't have the precision of measuring where that ball lands that would be needed for us to actually be able to tell the difference. So not only do we not need to do it, but it wouldn't help us at all. It just wouldn't help us do it. And it would also make it impossible to do the calculation. So it's very useful to focus on what we call these effective theories. So the reason I say this is because at any given scale, at any given time, we know about some of the laws of science. Right now we know about something called the standard model of particle physics, which tells us about matter's most basic elements and the forces through which they interact. But it's not the ultimate answer to everything. Ultimately, we want to go beyond it and understand some of the questions I'm going to tell you about. Will that make the standard model wrong? No, absolutely not. The standard model has been extremely well tested over the distances and energies with which it's been studied so far. But it could be part of a richer theory that underlies it, and that's what we're looking for today. So I said this already, but I just want to make sure everyone has the lay of the land. So we have atomic structure, so we have a nucleus, which is really a tiny nucleus surrounded by electrons. Most of the atoms are basically empty space. You'd never know it to look at this solid tabletop, but most of it is empty space. And you really had to get these tools to be able to see that. And inside the nucleus, we have protons and neutrons, indicated by the plus and the just neutral things. And that proton is made up of 2 up quarks and a down quark. Those are what are called the light quarks. There are heavier analogs of these light quarks. Those are not stable. They decay, and they decay very quickly. But we know about them because at high-energy colliders, they've been produced, and we've seen their consequences. And I have to say I find this quote really amusing. When I wrote my first book, Warp Passages, I did reflect on the fact that I actually didn't read a lot of these popular science books, so maybe I should go find out what they were like. So I asked people who did read them what were the ones they liked, and one of the ones they suggested was George Gamo's 1, 2, 3 Infinity, which is quite a nice book, written in 1947, so quite some time ago. He was a nuclear physicist, so he was someone who lived in the age where they had understood the nucleus to be composed of these smaller elements, protons and neutrons. And it's a really great quote because it works very well as both an idea of expressing why you get excited about these things, but also sort of as a cautionary tale. So what he said is, instead of a rather large number of indivisible atoms of classical physics, we are left with only 3 essentially different entities: protons, electrons, and neutrons. So he was very excited because they had understood a further level of substructure of the nucleus, and that was very useful to understand for many reasons. I mean, it was really the nuclear age that he was about to be living in. But he continued with his quote, and it says, "Thus it seems we have actually hit the bottom in our search for the basic elements of which matter is formed." Now, I hope I've said enough that you at least see some of the irony in this. He was someone who was so excited that they had just discovered this substructure, yet he didn't have the foresight to realize that this substructure that they discovered was limited by the distances that they could study at the time, and also the theoretical tools at their disposal. And of course, not all that long afterward, the substructure of protons and neutrons, namely the quarks held together by these gluons, was discovered. And I say this because it's very easy to scoff with hindsight, but at any given time, we really do tend to think we know all the answers. Why are we going beyond this? This all works so well. Yet every time we've been able to develop tools to go beyond, new and exciting things have been discovered. And that's what motivates us today. And as I said, today's frontier energy scale is a scale of 10 to the minus 19th meters. Particle physicists measure energies in what's called electron volts. So this is known as the TeV scale. Just to set it in context, if we use E equals mc squared, it's about 1,000 times the proton mass. So it's an energy 1,000 times bigger than that you would need to make a proton. Actually, this collider will actually have what's known as 14 TeV center of mass energy. So each of the beams will have so each of these beams of protons will carry 7 TeV of energy. So we're probing higher energy scales at this machine. I'll give you some idea of what we can learn there. The reason we need such high energy is because the things that collide are not really the protons. In some sense, it's the quarks inside that are colliding. It's the more elementary objects. It's like you're colliding together two bean bags, but you're really looking at the collisions of the beans inside. So those quarks themselves don't carry the full energy. So they will, in general, carry less than the 7 TeV energy. So if you want to learn about things that happen at center of mass energies of a few TeV, you need to have an even higher energy collision when you collide together these protons. And this is a nice video that someone on what's called the ATLAS experiment made. It's one of the experiments that studies what happens at the Large Hadron Collider. So this is the tunnel. You can actually go visit this, and within the next couple of years, it's going to be closed down. It's going to close down at the end of the year. So I suggest you visit if you want to see it, because then you can go visit the experiments. Things are not running, so you can go see stuff. Protons collide. They get accelerated around the ring. They collide together. And where they collide together, these experiments, like the ATLAS experiment, are built concentrically around it. So the particles collide. They turn into other particles. They come out. They spray out. And then these detectors, namely the ATLAS detector, CMS detector, and others, are designed around them to measure everything they can. Any of the properties that are accessible, such as energy, momentum, which directions the tracks went in. The tracks are these particle lines. What are the charges? Do they interact on the strong nuclear force? They measure everything they can as precisely as possible. And I mean, these experiments are really impressive to see. And I wasn't joking when I said if you're near Geneva, you should visit. I should have said that the Large Hadron Collider is located at a facility called CERN near Geneva. And it really is quite impressive when you go visit, because you can see these enormous detectors laid out. And at that time, they'll be dismantled a little bit, so you can see the different elements of them. And the thing, I always say, like, we're from New York, it's like big, so what? But the exciting thing is not just that it's big, it's that it's measuring things with micron precision. So it's measuring things incredibly precisely. So you have this enormous machine which is designed to measure all these elementary particles at this incredible level of precision. And the reason you do that is because most of the time you have junk that comes out. That is to say, it's standard model stuff that you would know about. But like 1 out of a trillion times, something new can happen. And you have to be able to figure out what it is. Did it decay into standard model particles? What standard model particles were there, and how can you tell them apart? Okay. So I'm just going to tell you a little bit more about the LHC. It's very cool. I mean, I'm not one that gets too excited by technology. But when you go to visit and hear the stories from the experimenters, everything that went into what goes on to build these things, it's really impressive. But just in terms of the machine itself, it's important that it will have the highest energy. It already does have the highest energy. Right now, it's running at 8 TeV center mass energy. Like I said, the goal is 14 TeV. So it's going to shut down at the end of the year. They're going to redo everything, make sure it's all okay, and turn it back on in about 1.5 years. And hopefully it'll be running at close to 14 TeV center mass energy then. So it'll reach this higher energy. And that's 7 times the energy that the Tevatron, which you might have heard of, that just closed down in Batavia, Illinois. That was the American machine. That was the previous highest energy machine that existed. It also will have the highest what's called luminosity. Luminosity is basically a measure of intensity. And the idea is to have as many collisions as possible. You're looking for these very rare events, so you want to collide together as many things as possible so you have a chance of seeing something. It's like buying more lottery tickets to increase your odds of winning. And then there's a whole bunch of technology that I'm not going to go into that goes into making this thing work. In particular, it requires superconducting technology. It required the strongest magnets in production. So there's a lot of amazing things that go into that. You need it to be very cold, in fact, colder than outer space. You need it to be a very effective vacuum because you don't want to have things colliding and quenching these magnets. So it's just an incredibly impressive machine. Okay. What will we learn there? As physicists, what do we care about? Well, there's a few questions that really drive what we're thinking about when we think about the Large Hadron Collider. And this is sort of the theories that we hope to study and hope to understand from the results. So there's a big interaction between theorists and experimenters now, because we have ideas about what you should look for, then they go and look for it. And it's not done the way you do with telescopes, where you have to point in a particular direction. Really, they're measuring everything they can. If you say this could be something interesting, the hope is they will record it. And then afterward, there's like analysis groups that split up and try to figure out, does it match this theory? Does it match this theory? We saw this weird thing. Does it look like this? This theory predicts this weird thing. We didn't see it. Does that rule out that theory? So they're really testing many ideas at the same time, which means that we, as theorists, can work on many ideas at the same time, even if they contradict each other. Because these experiments are so difficult that if we don't tell them what to look for, they won't find it. So we really want to have, that doesn't mean we have to know everything, get every detail right, but we have to know what qualitatively will distinguish the new things from the old things. Okay. What are they going to look for? Well, they're going to look for something called the Higgs boson, which, so again, as many of you might have heard of. There was a lot of hints of a Higgs boson announced last December. And what that tells us, we hope, is how elementary particles acquire their masses. Elementary particles, if they had masses from the get-go, you would end up making nonsensical predictions, like probabilities of collisions greater than 1 at high energies, things that just don't make sense. So even though it seems so obvious that these particles have masses, after all, the electron has a mass and gets bound into an atom, it turns out that there has to be some mechanism underlying that, some mechanism that tells us where these particle masses came from. And that mechanism is known as the Higgs mechanism. It tells us that empty space is actually more interesting than we think. It's a little bit like there's some charge that's spread throughout empty space, and particles acquire their mass by interacting with that charge. Heavier particles interact more, lighter particles interact less. So that is the Higgs mechanism. And most physicists, I would say, think the Higgs mechanism is right and really does account for particle masses. But we would really like more conclusive experimental evidence, something that really tells us this Higgs mechanism is right. And also something that tells us how it's implemented. And this is important because this distinction is often lost. There are sort of two things. There's the mechanism that tells us this charge is out there and particles get their masses. But then there's the sector of the theory that implements it, which might involve this particle called the Higgs boson. Okay? So the Higgs boson is something, if it's there, we also know its particles really well, its properties really well, because it's, again, related to the simplest implementation of the Higgs mechanism, which means that Higgs boson interacts more with heavier particles and less with light ones. So experimenters know precisely what to look for. And so what they found or announced in December were hints that they had seen a particle of a particular mass that decays into different particles at more or less the rates they should. Okay? Is that right? Have they discovered the Higgs boson? We don't know. I think most physicists think the probability is greater than 1/2, but I don't think we'd say it's overwhelmingly greater than 1/2. They have hints of this, but really what's needed is more data. Fortunately, before they shut down at the end of the year, they will have more data, 4 times the amount of data. So by the end of the year, we really hope to find out whether indeed these experiments have discovered the Higgs boson or not. Now, a lot of people are worried, what if they don't discover the Higgs boson? Does that mean everything is wrong and we have to throw up our hands and just go home? Well, no, because as I said, the Higgs boson is associated with one particular way of implementing the Higgs mechanism. There could be other ways, and it means that the searches will be more challenging, but we also have ideas of what they would look for in those cases. So the Higgs boson would certainly be conclusive proof that the Higgs mechanism is right, and it would tell us how it's implemented, but if we don't see it, it's not conclusive proof that the Higgs mechanism is wrong. It just means the searches are more challenging. Okay. Yes, question?
I'm just wondering, when you say elementary particles, how they acquire mass from the get-go, what time how is time factoring into that? Where are you measuring?
That's a fine question. So one way of thinking of it, the question is, basically, what do I mean by particles acquiring their masses? Like, when is this happening, essentially? Is that fair? So One way of thinking about it is that in the early universe, when the temperature is really hot, in some sense these particles don't have masses. They're like massless, they're radiation. Later on, there's a phase transition. So at that point, you don't have this charge spread throughout space. But probably at some lower temperature, which is essentially the energy scale that the Large Hadron Collider operates at that temperature, there's a phase transition. When that phase transition happens, then the charge gets spread throughout the vacuum and particles acquire their masses. From the point of view of what's happening today, though, we just know that it's there. The temperature isn't changing. The Higgs mechanism has occurred. This transition has happened. Everything is out there. So again, I say this because people are sometimes confused. Like, if you don't find the Higgs boson, does that mean particles don't have masses? No, because it's a particle on top of the vacuum state, which has no particles. So there's a vacuum state that has no particles, responsible for giving masses. And then the experimental evidence is this fluctuation, which is the particle known as the Higgs boson. Since one person was brave enough to raise her hand, I will just pause and ask if there are any other questions before I go on. Yes?
You can save for much later. You were talking about scales. In 1988, Margaret Geller took me on a ride on a Cray computer out to the Great Wall at the end of space. Instrumentation today cannot see in the macro level, I don't think, much beyond that. How do we know that there isn't some it keeps going and going, and like the quantum universe, the macro universe keeps going and going, and that maybe it is like the quantum universe on a macro scale, that there are forces that we cannot see or find yet because it may go beyond our capability.
So again, I refer to the fact that I was talking about what we can measure when I said that slide. And there could be a universe much bigger than what we can see. Now, of course, if there were forces on a bigger scale, you'd have to be careful, because a lot of the time if they're on a big scale, they would have some effect on a smaller scale. But you can imagine some very weak force that you have to go over a very long distance to see its effects. We just can't say anything about it right now. And it's also, I mean, most of the way forces act, that's not usually how they act, but it's not out of the questions that something like that can happen. But we would have theories about it, but we don't necessarily have experimental data to back it up. Yeah. Okay.
Would you explain to the audience what phase transition is?
Okay, a phase transition is like ice to water. So it's basically you have one state of matter that turns into another state of matter. That is a phase transition on my computer. So I'm going to very quickly run through the slides and answer questions later, because it's going to shut off in a second. And I'm going to go to only the important things. Well, I do want to say that one of the other things we're going to talk about, and I can say this without the slide, is understanding the weakness of gravity, and we're going to come to that, and dark matter. So I'm going to come back to that. Sorry about this. I'm going to see if there's any cool. So this is the rest of that video, so I want to show that. And this actually shows the particles going through the different layers of the detector, so that we can identify a particle. And like I said, each of these different layers is measuring something different. Sometimes we're measuring tracks, sometimes we're measuring energy. And in this case, it's used to identify what's called a standard model particle, known as a Z boson. And I'm saying all of this really quickly because all these videos are about to disappear. Okay. Sorry, so I'm just going to talk at this point. I apologize for this. I could put another battery in, but by the time it rebooted, it would be pretty late. So if it's okay with you, I'm just going to talk for a little bit. But I can, therefore, answer questions. So anyway, the phase transition in this case that we're talking about is the phase transition between what's called a Higgs field. So it's one more term I'm introducing now. So I said there's a vacuum. A Higgs field is something spread in that vacuum. It's not particles. It's just a field. So in some sense, you can think of it as a bunch of charges. So it's a transition between no charge and having charge spread throughout the vacuum, which is the state with no particles. That's what I meant. Okay. Other questions? Yes?
Earlier you referred to the start of the universe, I guess the Big Bang or the Standard Model, 13 billion point whatever. But what happened before that time? I mean, this is a question about finite infinite. If there's a set time or a set... So
again, I'm really making a point here of emphasizing things that we can measure and say things about. So you can make it up whatever you want about that time. But we really don't know the answers.
Ex nihilo, like the Bible, creation out of nothing at a point in time.
It sounds like it, but one little secret about the Big Bang Theory, well, I'll tell you two secrets about the Big Bang Theory. One is that the name was a facetious name that someone was making fun of the theory came up with. And the other is that the Big Bang Theory tells you about the late evolution of the universe, but it tells you everything except about the bang. That's not what it's about. It's about telling you how the universe evolves. And to understand the bang, you really need to know more, both theoretically and perhaps experimentally. We actually don't know the answer to that question. It really is just subjective speculation.
So it might be an infinite universe.
It very likely is an infinite universe, and it could be that universes are being created at different times in different places. We just don't have any contact with them, or we won't know about it.
And why was he negative about quantum physics?
Because it's crazy. Because it's really hard to understand quantum physics. I mean, it just doesn't seem intuitive. But more seriously, it's because he really wanted to believe that everything was predictive, and there is some randomness in it. In a sense, there really is probabilities. There really are probabilities involved when we describe what quantum mechanics tells us. So, so since I didn't finish my talk, I'm actually going to spend.
I was just going to make sure it goes on to other people, if you would.
Oh, okay. Oh, okay. Thanks. I thought I would actually just say a few more words before I answer more questions. Okay. Okay. Well, take that off. Actually, I could put another battery in just in case people want to hear it. But. Okay. Well, I'm waiting. Okay. So, so what else does the Large Hadron Collider do? Well, I told you that we're trying to understand how elementary particles acquire their masses, but we also want to understand why those masses are what they are. Why aren't they 16 orders of magnitude bigger? You might say, why should I think they're 16 orders of magnitude bigger? Well, it turns out that according to our theories of quantum mechanics and quantum field, what's called quantum field theory, which combines together special relativity and quantum mechanics, you can actually calculate quantum corrections to that mass. I'm not going to tell you what that means. I'm just going to tell you that you can do a calculation involving quantum mechanics. And according to that calculation, you would expect masses to be 16 orders of magnitude bigger. Now, it doesn't mean they really are, but it means that if you have nothing else in the theory, you would need a fudge, what we call a fine-tuning, at the level of 16 digits of precision. Now, no one believes that's what's happening. I mean, physicists don't believe that's what's happening. This fine-tuning is just an artifact that we use to continue and use the standard model. But what we really think it means is that there's something deeper and richer that exists beyond the standard model. So in addition to the Higgs boson, even if it's found, we expect there to be some much more interesting sector of the theory. It turns out this is a really hard problem to solve. And the best explanations turn out to involve some pretty exotic things, like an extension of space-time symmetry. A space-time symmetry is a symmetry like rotation that says physics is the same in every direction. So an extension of space-time symmetry into the quantum regime. So that would be very exotic, and that's what's known as supersymmetry, which some of you have heard about. And so at the Large Hadron Collider, what supersymmetry would predict for every particle, there's a partner particle, and so at the Large Hadron Collider, they're looking for these partner particles. Another exotic idea that Lewis mentioned is an idea involving an extra dimension of space, beyond the three that we know about: forward, backward, left, right, up, down. You might say, how could there be other dimensions? I don't see any other dimensions. But I think you realize by now that there's lots of things we don't see. So it came out much quicker than I thought it would. Okay, so there's many things that we don't see, and many things we can hope to learn about. And one of them could be an extra dimension of space. Now, why do we think about that in this context? Well, in this context, the reason we think about it is because it turns out that this question of why masses are so much lighter than they are has an equivalent formulation in terms of why is gravity as weak as it is. So one of the other things we can hope to learn about at the Large Hadron Collider is potentially whether an extra dimension of space explains why gravity is so weak. And even though that seems like a very exotic idea, and even though I worked on it and developed it, I agree it is, the really exciting thing is that it will have experimental consequences. So when we're looking for this question of what resolves this question of the weakness of gravity, we really are, it's really quite interesting, because we really are possibly probing the nature of space and time, in addition to just looking at particles. And the final thing that, I mean, the Large Hadron Collider might tell us things we didn't expect at all, but the final thing we hope it will tell us about is possibly dark matter. Now you might say, why dark matter? That's completely off base. Why, we've been talking about things that happen at 10 to the minus 19 meters. Why dark matter? First of all, what is dark matter? Dark matter is matter it's matter, it's stuff that clumps, it interacts gravitationally just like matter, but it doesn't interact with light. So technically speaking, it's not dark, it's transparent. As you know, I can see a lot of dark things, like I can see this jacket because it absorbs light. So really it's transparent matter. So it's matter that doesn't interact with light. So why do we think we have a chance of saying anything about it at the Large Hadron Collider? Well, it turns out that a particle that's stable, that has a mass such that we can make it at the Large Hadron Collider, has this really interesting property. If I just traced what happens as the universe evolves over time, as it cools down, and just trace how much of it is left today, I would find that the amount of energy left in dark matter is just about right. Now, this could just be a coincidence of numbers, but it has led people to think that maybe this is a hint that really it has something to do with the physics that's happening at this scale. Maybe even this physics that's explaining masses or explaining why masses are what they are. And that's what's being looked for today. So those are the things we're looking for. So I'm just going to pick this up a little bit. Okay. So I'll pick it up where I had this video. I think I can, this extra battery actually worked. But I think I'm almost out of time anyway. I will skip that now. And this is proof I was actually visiting, as you can do too. And this was this idea about the extra dimension of space that I've been telling you about. And since it was mentioned, I will mention this idea of a brain world. The idea that even if there is an extra dimension of space, we don't necessarily travel in it. We can be stuck on a lower dimensional surface known as a brain. The brain stems from the word membrane. So our theory was based on the idea that we, and all the forces we know about, except for gravity, actually live on a brain. And if you have two of these brains and you just solve Einstein's equations of gravity, he tells us exactly what the gravity is given the energy distribution. And if we solved it, Raman Sundram and I solved this, and what we found is that in some sense the strength of gravity varies exponentially, extremely quickly, as you go from one of these brains to the other. So if you think of this question of why gravity is so weak as it is, the answer is that we just don't live where gravity is concentrated. We live a modest distance away, but it's exponentially smaller where we are. Okay. Another way of thinking about it is that in this warp geometry, and that's called warp geometry, things vary exponentially as you go out, and they vary in such a way that sort of sizes and masses are rescaled. So if we ask the question, why are masses as light as they are, it's because we're living on the weak brain. Had we lived on the gravity brain, they would have indeed have been 16 orders of magnitude heavier. And as I said, the reason we think it's worth paying attention to this is actually something that is being looked for at the Large Hadron Collider. In particular, what happens is you can collide together protons. You can make a particle called a Kaluza-Klein particle. It's named after two of the people who thought about extra dimensions in the context of physics in the early 20th century. What they are particles like the ones we know about, but they carry momentum in another dimension. We don't actually see the other dimension, so we interpret that as heavy particles with properties like particles of the ones we know about. And if it's produced in this case, it will decay in the detector just like that Z boson did, and we'll be able to measure what it decays into and thereby find what was there. And by looking at various decay modes, you can see, does it have precisely the properties we would predict for this Kaluza-Klein partner of, in this case, the graviton, the particle that communicates gravity. So I'll just end by getting back to the little bit of artistic stuff. I'm just racing through this now because I know there's some questions, but I just want to have some fun. So I just want to say that some of the things we did were, because after I wrote the first book and after I did this, a lot of people in other creative fields contacted me because they were very excited about the idea of seeing physics incorporated into it. And in particular, two of the things I thought were interesting enough to actually get involved in were one that was this projective opera that I mentioned earlier that premiered at the Frumkes Center, and the other was an art show based on the notion of scale. And the reason I did the art show, because a lot of people try to do things about art and science, but then the question is, what is it? Are you trying to have art reproduce science? Are you trying to have science that has pretty pictures? And so what we decided to do was just to have a theme that resonated both with artists and scientists. In particular, as you can imagine, I like the theme of scale. So what these artists did, and I don't have very many examples here, but you can look it up on the web, is they sort of had various projects where they had very different things happening at small scales and at big scales. So this one's probably the most literal that's on this poster, We called it Measure for Measure. And it was at the Los Angeles, it started off in the Los Angeles Art Association. Went to Chapman and Harvard. But what you don't see in this picture is that what she did is she took very detailed photos at a very small scale, a little bit like the Eiffel Tower that we saw earlier, and they put together to make this picture. And this was probably one of the more literal examples, but there were many examples of this in the art show, and it was really a lot of fun. The other thing was this opera that I mentioned, so I'll just spend a couple of minutes just letting you hear some of the music and see what it looked like. So it was in Frumkes Center, so it was translated into French. He lived in a smaller, more gray world. She was in a more colorful, more expansive world, which was the higher dimension. We had a challenging geometric problem, which is we didn't have an orchestra pit. Where do you put the orchestra? We had the Ensemble Intercontemporain. So they were behind this translucent screen. Hector insisted on there being actual physics, so there's actually an equation she sang, which I had him pick out because I thought it was ridiculous, but it worked very well. And then she's discovering this extra-dimensional world. And then they're trying to talk to each other and communicate. And one of the other things I want to get across with this was not just the physics, but also just what goes into discovery, what goes into creativity, and how it's sort of based on thinking you actually don't know everything that's there. And in this case, it's sort of how do you communicate between someone who can actually explore this extra dimension and someone who gets the indirect evidence, which is, of course, us. I mean, we don't directly go out and see all these things. We don't go out and visit the world of atoms, but they do come back and give us evidence that we can see in experiments. So as I said, there are sort of two themes in the book. One is scientific thinking. Of course, the role of scale, but a lot of other things go into scientific thinking, and creativity and beauty. What's the role of beauty? And also what we explore today, both in terms of the Large Hadron Collider and dark matter. So I think we have a lot to learn, but we've learned an awful lot so far. And so I'll just close with one final slide, which is a picture I saw in the Tate, which I think very nicely expresses the idea that the world can be a lot richer than the world we think we're living in. And what I didn't know at the time was this is actually the Chateau de Sion, which is located very close to CERN, which is where the Large Hadron Collider is. So obviously that's not a coincidence. Thank you.
Thank you, Lisa, for a wonderful talk. Now we'll take some questions. Lady right here.
Yes, I wonder if you could comment on the, oh, thank you.
So everyone can hear.
I wonder if you can comment on the current talk about a multiverse world and what led to positing this possibility.
Sorry, I'm just going to first start. This makes me laugh because I just had a bunch of interviews last week because my German translation came out. And I had one interview that was about religion and science and about the multiverse. They kept asking me about the multiverse. And they kept saying, well, we know you're not that interested in the multiverse, but we're going to ask you about it anyway. And like basically 90% of the way through the interview, they said, oh, by the way, he's very religious and his father's a priest. And then they said, oh, and by the way, 2 years ago we wrote a book about the multiverse. So I felt like I've been fooled. But I think, so there's reasons people think about the multiverse, but it's important to think about it in this context. I mean, we don't know the multiverse exists. It's purely a theoretical construct, and it might well exist. And what it would say is that there are different universes that we don't interact with, that have different properties. One of the reasons people started thinking about it was because we do have this puzzle. In addition to dark matter, there's a puzzle of what's called dark energy, which is energy not actually carried by matter. And it's a very mysterious thing, because it's not at zero energy, but it's not nearly as big as you would expect it to be. And no one has come up with a physics explanation from first principles why this is the way it should be. So people think about it in the context of what's called the anthropic principle. This is the only energy we can have in a universe that would support galaxies. But in order for that to be true, you need to have you have to have all these different universes populated so that you can actually find the right one. The other reason people have thought about it is because people working on string theory, which I didn't talk a lot about, found many different possible solutions. It used to be thought that string theory will predict everything. We'll know what it is. We can predict, it's a unit prediction from this universe. But now there are many possibilities that people discovered. And also from the point of view of cosmological inflation, it looks like you might populate all of these. So there are several theoretical reasons that have led people to think about the multiverse. But I think also in the popular imagination, people just like it. And also, you don't have to understand a whole lot of science to think about it, so they often like thinking about it.
Next. In the back.
Yeah, the work that physics does deals with how things work, but does any of your work deal with why, or answer Leibniz's question, why is there a world rather than nothing at all?
Well, I mean, there's answers in terms of inflation, and there's other answers, but I mean, there are only certain questions that physics will ever answer. I mean, they can trace how things happen. I think science in general doesn't do very well with origin questions. I mean, when we talk about evolution, we forget that, right? It's not that evolution explains how life started, it explains how it evolved. Big Bang Theory explains how it evolves. So people will tell you that there are answers to these questions, but I'm not sure we will ever really know those answers from science, is the fact.
The gentleman here. You.
Getting back to the string theory, is string theory, the 10 dimensions in string theory, are they just a mathematical construct, or is there some real relationship to the...
Well, this is exactly why I emphasize this idea of effective theories. It could be that it underlies everything, or it could be that it's a mathematical construct. We don't know, because we are not probing the scales 16 orders of magnitude smaller than what we're studying, which we would need to study that. I mean, some of the things we think about have elements that come out of string theory, but we're not directly testing string theory. It's just motivating certain interesting theories. It's very hard to, I mean, if this warp geometry is right, it could be that there are string modes that would be at much more accessible energies, but we would have to be very lucky for that to be the case. In general, if gravity is the way we expect it to be, or used to think about it, it really requires 16 orders of magnitude of energy beyond what we've achieved so far. That's why we say. So there's two ways to think about that. One is that the strings themselves are 16 orders of magnitude, so too small, so they just look like particles. We can't tell the difference. And another way to think about it is the way you tell the difference between a string and a particle is that a string can oscillate in many different ways. So there could be different particles. But if you need 16 orders of magnitude more energy to make those particles, you never make them. So you can't tell that they're there.
Over there.
Is gravity qualitatively different from the other forces? And like electromagnetism is mediated by an exchange of photons. Is gravity not mediated?
Gravity we think gravity is mediated by the exchange of particles called gravitons. However, they're extremely weakly interacting, so weakly interacting, we don't know how to find them.
Are they part of the standard model?
A lot of the time people leave out gravity when they're talking about the standard model. It's not that we don't think it exists, it's just that it's so weak we can ignore it. So it's part of the physics of the underlying theory. Yeah.
I want to thank Lisa for a wonderful talk.